Okay, so let's look at this first question here. And what we're going to be doing is we're going to be figuring out what the area under the curve is of the given function. So the given function is going to be this linear equation here. And that function would this is integrating, and this is going to be called integrand. So this blue line here is the equation y is equal to negative 2x plus 3. And what we're going to be doing is we're going to be integrating this function from negative 2 to 1. That's going to give you the interval that I want you to find the area under. So remember that from yesterday's lesson, the interval is from a to b. So from a to b. So the interval, according to the way that this integral is set up, is from negative 2 to 1. Okay, so a is going to be negative 2 and b is going to be 1. So what they have is they've got the function set up. So here's the linear function here with a y-intercept of 3. And area from negative 2 to 1. So the area under the curve, remember, calculate this area here. And we're going to do it in several different methods. The first method that we're going to do is going to be the longest method, and it's what we did yesterday. And this is going to be, the method is going to be using the limit definition of the definite integral. Okay, so what was the limit definition of the definite integral? So what the definition was the area under the curve on the given interval. It's equal to the limit as n approaches infinity. And what we are going to sum is we're going to sum the area of infinite rectangles. So we're going to start from I is equal to 1 to infinity. And remember that the area of one rectangle is delta x. Delta x is the width of your rectangle times f of x sub I, and x sub I is the height of your rectangle. So this formula here, delta x times f of x sub I, gives you the area of one rectangle. Then we're going to use our summation formula to sum up infinite rectangles. That will give us the area under the curve from negative 2 to 1. So how we did this in yesterday's lesson is the first thing that we always calculate is we calculate the width. So width, remember, is delta x. Now you need to know what the formula for width is. Delta x, which is the width, is b minus a over n. Okay, so delta x is equal to b minus a, so 1 minus negative 2 over n. And delta x is 3 over n. Now, that should make sense to you, right? Because if I said to you, what is the width of this subinterval? The width here is 3 units, right? That would be 3. And then we would divide it by, so this 3, what that is giving you, that's giving you the width of the subinterval. And our subinterval was from negative 2 to 1. N is going to be the number of subintervals, or the number of rectangles. So number of subintervals. So if I divided this into 3 subintervals, into 3 rectangles, I would have a width of 1. We're going to try to get n to approach infinity. And then what we want by doing that is our width would approach 0. The more rectangles we could get, the better our approximation for area will be. So the second step after we calculate width is to calculate the height. Now the height of a rectangle is given by the function when we sub in x sub I. So it's f of x sub I. So from here, what you have to do is you first have to figure out what x sub I is. And x sub I, it's going to be, the formula is a plus I delta x. So a is where we're starting. right? So we're starting at negative 2. So x sub I is negative 2 plus, so delta x is 3 over n, and we're going to multiply that by I. Then we're going to input x sub I into our function. So we're going to input, and we're going to calculate what is f of negative 2 plus 3I over n. So input that into our function. The function is given by the linear equation y is equal to negative 2x plus 3. So take out your x and put in your x sub I. So it's going to be negative 2. And then we're going to sub in negative 2 plus 3I over n plus 3. Okay, f of x sub I is equal to, so this is going to be the height of our rectangle. We're going to use algebra to distribute the negative 2 inside. And we will get 4 minus 6I over n plus 3. And f of x sub I is going to be 7 minus 6I over n. Okay, so now we're going to input our width and our height into the limit definition. So the area is equal to the limit as n approaches infinity. And we're going to be summing up from 1 to n of delta x. So delta x is the width of my rectangle, which is 3 over n, times the height of the rectangle. And the height of the rectangle is f of x sub I. Okay, so you set up your limit. From here, let's expand the 3 over n into the binomial. And we will get 21 over n minus 18I over n. Use your properties of limits to separate this into two separate summations. Yes, sorry, n times n is n squared. So we're going to have 21 over n, and then we're going to sum and we'll have 18I over n squared. Okay, so remember from yesterday, what the goal is we want to try to get I squareds or I cubes, because then we could replace it with the formula for the sum of consecutive numbers or the sum of squares or the sum of cubes. So I want to isolate that I to replace with the formula. So what that means is I'm going to bring this 18 over n squared in front of the summation. Over here, I don't have an I squared or an I cubed, so I want to keep the 21 there because I know what the summation of a constant is. It's c times n. So what I'm going to bring is I'm going to bring 1 over n to the front. So area is equal to the limit as n approaches infinity of 1 over n. And then I've got a constant of 21 here. Okay, so now what we're going to do is we're going to replace 21 with our summing summing a constant, so n times c, and we're going to replace I with the sum of consecutive integers. You're going to replace these two with their formulas. So that would give us the limit as n approaches infinity of 1 over n. The formula for a constant is c times n, but c is 21. So I'm going to just bring that 21 down. N over n will cancel. So the area is going to be 21 minus 18 over n squared. Replace I, formula for I, sum of consecutive numbers, over 6, oh, over 2, thank you. Okay, so from here, n, and that would cancel. 2 goes into 2 once, 2 goes into 18 9 times, and I'm going to distribute this inside. So I'm going to get the area is equal to the limit as n approaches infinity of 21 minus 9n plus 9 over n. Then you're going to take this part of the limit and you're going to divide each term, Emily, by what? By n. You're going to divide each term by the highest power in the denominator, which would be n. So I would divide this by n, this by n, and this by n. And what that would give me is the limit as n approaches infinity of 21 minus 9 plus 9 over n all over 1. As the number of rectangles approaches infinity, that will approach 0. So the area is going to be 21 minus 9, which is what? Okay, so the area is going to be under the curve on the interval -2 to 1. It's going to be 12. So using the limit definition will get us the answer. It's going to be the most complex way. We're going to do this 3 more times and get the same number of 12. Page. One up here, this is when we're going to do antiderivatives. We'll do the fundamental theorem of calculus with this one. It's the same thing I've written down 4 different times. So again, how could I interpret this? This is whenever you see this symbol, this is the area under the curve. This represents my curve. So this is going to be f of x. We're going to be integrating with respect to dx. So it's the area under the curve. The curve is y is equal to -2x plus 3 on the interval. So this is going to give us my interval from -2 to 1. Always to be is this will be our A, and this is going to be our B. Okay, so we've got the exact same area under the curve, and now let's use some geometric shapes to quickly calculate the area. So if I'm looking at this region here, I could easily calculate the area of this rectangle. The width of this rectangle is 3. The height of this rectangle is 1. So the area of this rectangle, 3 times 1, is 3. And then what geometric shape would I use to calculate this remaining area? It would be a triangle. So this geometric shape would be the area of a triangle. So let's calculate what the area of this triangle will be. So we know that the area of a triangle is base times height divided by 2. The base of this triangle is 3 units. The height of this triangle is 1, 2, 3, 4, 5, 6. So 3 times 6 divided by 2. The area of this triangle is 9. So the area under the curve is a triangle plus the rectangle. It's going to be 12. So the answer is 12. Now what we're going to do is we're going to do the fundamental theorem of calculus, which is what this lesson is on. So I'm just going to go back and I'm just going to show you up here what the fundamental theorem of calculus is. If f of x, our function is linear, is continuous on the closed interval a to b, then what the fundamental theorem of calculus says is it says that we could integrate, so this is we're integrating the area under the curve from a to b. So actually, if you could just flip back to this page, I'm going to tell you what a is called and what b is called. So a is our lower limit of integration. So a is the lower limit of integration. B is what we call the upper limit of integration. This symbol, this S, it's like for sum, this is the integral symbol. So this is the integral of f of x dx. We're integrating with respect to x from a to b. So from this lower limit of integration to the upper limit of integration. And what the fundamental theorem of calculus is going to be is it says is if we are integrating and f of x is continuous on the closed interval from a to b, then what it's going to equal is f of b minus f of a. Now you need to know what f of b and f of a are. So f of x is our function. What f of b is, it is the antiderivative of this function evaluated at b. So big F of b, let's just mark this. Big F of b is the antiderivative. So it's the antiderivative of f of x. So we're going to have to find the antiderivative. We're going to have to go back to lesson 1. The antiderivative of f of x evaluated at the upper limit of integration. So we evaluated at the upper limit of integration, which is whatever value b is on our interval. And then what f of a would be, f of a is going to be the antiderivative of that function evaluated at the lower limit of integration. Okay, so how are we going to use this? I'm going to show you the long method for the fundamental theorem of calculus, and then I'm going to show you the work that I would expect, which is going to be much less than this long method. Okay, so we've got the exact same function that we're evaluating from -2 to 1. So again, -2 to 1. This is a to b. So -2 is a, this is b. According to the fundamental theorem of calculus, it's going to be f of b minus f of a. Okay, so first we need to figure out what our function is. This is our function, f of x. So f of x is -2x plus 3. Then we figure out what the antiderivative of f of x is. So we have to go back to lesson 1. And when we want to figure out the antiderivative of f of x, how we're going to write that is big F of x. So the antiderivative, and how we're going to do that is when we want the antiderivative of this function, we're going to use the reverse power rule. So remember how we do that? We're going to add 1 to the exponent and then divide by that exponent. So this would be -2x. If I add 1, it'd be 2 divided by 2. This guy is x to the 0. So remember, we're going to add 1. So this will be 3x over 1. And then we're going to put the plus c, the constant of integration. We'll only do the plus c for this one example because I'm going to show you how we actually don't need, when we're evaluating different integrals, this constant of integration because it's going to cancel. But f of x is equal to -x squared. So the antiderivative of this function is -x squared plus 3x plus c. Okay, So what we need to do in order to do the fundamental theorem of calculus, we need to evaluate the antiderivative at b minus the antiderivative of a. So what that would be, it would be big F of my upper limit of integration is 1 minus big F, so the antiderivative evaluated at the lower limit of integration, which is negative 2. So once you figure out what your antiderivative is, big F of x, let's evaluate that at 1 and evaluate that at negative 2. Okay, so F of 1 is equal to negative, I'm going to put a 1 in here, so negative 1 squared will be negative 1 plus 3 plus the constant of integration. F of 1 is equal to 2 plus c. Evaluate what F of negative 2 is. So we're going to evaluate F of big F, the antiderivative, at the lower limit of integration, which is negative 2. So I have a negative, and then I'm going to have negative 2 squared, so that will give me negative 4. Plus, actually no, it'll be minus 6. 3 times negative 2 will be negative 6. Plus c. F of negative 2 is equal to negative 10 plus c. Okay, so according to the fundamental theorem of calculus, we're going to get the area under the curve if we evaluate f of 1 minus f of 2. So let's figure out what that is. So we want f of 1 minus f of 2. So f of 1 is 2 plus c minus f of 2. So binomial, put it in a bracket, so negative 10 plus c. The reason why we don't need to include our c's is because they will always cancel at this step. We'll have 2 plus c, and when you distribute in that negative, you're going to have plus 10 minus c. C will cancel, and we get an area of 12. Okay, so do I want you to show all of this work here? No. I'll show you what I would expect you to show and the notation that I would expect. Okay, so we're going to integrate this function with respect to x. So let's find the antiderivative. It's the same function. But what we're going to do is we're going to put it in a square bracket when you take the antiderivative. So the antiderivative of negative 2x, add 1 to the exponent, divide by 2. That's going to give us negative x squared. So same antiderivative plus 3x. We don't need to put the plus c for the constant of integration. And then you're going to put your lower and upper limit of integration. So we're going to put negative 2 here and 1 here. So when I see this notation, what this notation is telling me is that we have not yet substituted the upper and lower limits of integration into our antiderivative. Okay, so this is the antiderivative of the function. This is big F of x, but we have not yet substituted in the upper and lower limit of integration. So from here, we are going to calculate the f of b minus f of a, which will be f of 1 minus f a is negative 2. Okay, so into your antiderivative, you're going to sub in 1. So f of 1, you're just going to sub it in. So it would be negative 1. So f of 1 would be negative 1 plus 3 minus, create a bracket, and now the lower limit of integration, so sub in negative 2. So negative 2 squared would be negative 4 minus 6. From here, we get 2 minus negative 10, which is 12. So for the remaining problems that we're going to do, this is the work that we're going to show. Okay. Okay. I want you to integrate from 2 to 5 the area under this curve. So here's the curve. Here's from 2 to 5, and we're going to integrate it. So this is equal to, take the antiderivative of your function. Oh, all of these are going to actually have the same antiderivative because it's the same curve. It's the same function here. We're just changing our interval. So our interval for this one would be 2 to 5. We're integrating from 2 to 5. So it's going to be negative x squared plus 3x, and we're integrating from 2 until 5. So fundamental theorem of calculus says that if f of x is continuous on the closed interval, this is a continuous function from 2 to 5. It's going to be f of b minus f of a, and that's going to be f of 5 minus f of 2. From here, going to sub in your 5, which is your upper limit of integration, into your antiderivative. So it would be negative 25 plus 15 minus, when I sub in f of 2, make sure you just put that in a bracket. So it's going to be negative 4 plus 6. Okay, this is going to give me negative 10 minus 2. And this is going to give me an area of negative 12. So let's see if this makes sense. This shape, I don't know if you could sort of tell, it is the exact same as this, except it's just been reflected, and the shape is now below the x-axis. So this was 12 units. It would make sense that the exact same shape down here would be 12 units. Does anybody know why? What's different about this shape versus the shape that was, why would the shape be negative? It's below the x-axis. So the area here, the total area is 12, but what we do with integration is we use something called signed analysis when we're evaluating integrals. When we are below the x-axis, we consider that area to be negative area. Above the x-axis is always going to give us a positive area. Below the x-axis is always going to give us negative. Function now, so how we would evaluate this on our calculator, because all of these could be checked on your calculator. So if you have your calculators, integrals are under math and 9. And you're going to enter your lower and your upper limit of integration. So let's first do the one above the x-axis, which was from negative 2 to 1. Negative 2, type in 1. And we're integrating negative 2x plus with respect to x. And we got 12. Yes. So math, and then 9 is, and then 8, I'll show you later on, is your derivative. You could actually do derivatives on here. So now type in this one. So type in from 2 to 5 when we're integrating from 2 to 5. So 2 to 5 of negative 2x plus 3 with respect to x, we get negative 12 because that area is below the x-axis. So this is like, it's going to be called the net area, what we're going to be doing. Okay, so let's now do the exact same f of x. Are you getting it? Was it showing on yours? Oh, I'll look after. Okay, so you guys, before we integrate this one, from negative 1 to 4, are you able to look at this and say this is going to be a positive area, this is going to be negative area, and they're going to like think about what's going to happen for this one, okay? So let's integrate from negative 1 to 4. So let's take the antiderivative of our function using the reverse power rule. So that is going to give us negative x squared plus 3x. And we're going to integrate from negative 1 to 4. According to the fundamental theorem of calculus, it will be f of b minus f of a. A is my lower limit of integration, b is my upper limit of integration. So it's going to be f of negative 1 minus f of 4. And input negative 1. So negative 1 squared will give me 1, but that, and then I've got a negative in front. So it's going to be negative 1 minus 3 minus f of 4 will be negative 16 plus 12. Negative 4 minus, oh, yeah, what did I, f of b, thank you. Let's fix this. F of b, 4, f of 4 minus f of a. Okay, so f of 4, that's going to give us negative 16 plus 12 minus f of negative 1 will give me negative 1 minus 3. That will give me negative 4 minus negative 4. Negative 4 plus 4. Overall, I get a net area of 0. Okay? And the reason is the area above the x-axis is identical to the area below the x-axis. Because we're going to use signed analysis, this will be a positive area, this would be a negative area, and they're just canceling each other out. What do you think about this one? Overall, are we going to have, do we have more positive area or more negative area? Positive area. So what's actually going to happen is this shape, if you look here, that triangle will cancel with this triangle. And overall, we're going to have a net positive area. So the antiderivative is negative x squared plus 3x, integrating from negative 1 to 3. It's f of b minus f of a, f of 3 minus f of negative 1. F of 3 is negative 9 plus 9 minus f of negative 1 is negative 1 minus 3. 0 minus negative 4. And we're getting an overall net area of 4. And where the 4 would come from is if you actually count these squares, I'd have 1 square here, 2, 3, and then this and this would actually add up to our 4th square. Again, we could calculate that on our calculator, right? So math 9, and we're integrating from negative 1 to 3. And so we get 4 there. Okay, let's do one more. And then we'll look at different integrands. Overall net area, what do you guys think it'll be? Negative. So this area is going to match with this. So this area will be positive, this area will be negative, they will cancel. Overall, we're going to have a net negative area for this. So the antiderivative is negative x squared plus 3x. And the integral is from 0 to 5. F of 0, if you just put 0 into this antiderivative, we're going to get 0. So that will equal negative 25 plus 15 is negative 10 minus 0. It's going to give us a net area of negative 10, which should make sense, right? Overall, we have a net negative area. The amount of area below the x-axis is much larger than the amount of area above the x-axis. Okay, let's look at some different examples now. So evaluate the definite integral if it exists. One of these integrals will not exist on, so we'll see if we could figure out why it is. So if we integrate this first one, so add 1 to the exponent, divide by 2, that's going to give us x squared, minus, add 1 to the exponent, divide by the new exponent. This is going to give us x cubed over 3. And the integral is from negative 1 to 2. Okay, so let's calculate f of b. So we won't even write it. We'll just, from here I could plug in f of 2, big F of 2. So that's going to give me 4 minus, if I plug 2 here, 2 cubed is 8 over 3. Minus, so this is f of b minus, and now I'm going to do f of a. So negative 1 squared is 1. Minus negative 1 cubed will be negative 1. 2 negatives will give me a positive. So I'm going to have plus 1 over 3 equals. Now, instead of getting common denominators at this stage, I mean, you could, or you could see that this like 8 over 3 and 1/3 can actually be combined if I remove my brackets. So what I would have is I would have 4 minus 8/3, and then I would have minus 1 when I distribute that in, minus 1/3. This will give me 3 minus 9/3. That's not how I did. Let me just double check. 4 minus 8/3, 1 plus 1/3. And then we want to get common denominators. Yeah, wait a second. Why is that? Where's the mistake? So 4 minus 8/3 minus 1 is 1/3. Okay, let me actually just do something different. There's a mistake somewhere. 4 minus 8/3. So let's actually put common denominators here then. So 3, 3. Oh yeah, 0. Are you guys getting 0? Let's find our calculator. What's that? On the calculator? Oh, okay, yes. Yes, I didn't check this one. So from negative 1 to 2 of 2x minus x squared. Yeah, that's 0. Okay, so this one here. Watch what's going to happen with this one. Now, normally when we integrate, remember we don't have quotient law for integration. So what we want to do is we want to rewrite this as the definite integral from -2 to 3 of x to the -2. Okay, and we're integrating with respect to x. Then from here, it's really easy for students to say, okay, I know that the antiderivative of this, remember that you're going to add 1. So you're going to get x to the -1 divide by the exponent. And we're going to, from -2 to 3 is our integral. And then this is going to be -1 over x from -2 to 3. And then students would go from here and they would go f of b minus f of a. But there's going to be an issue. And the issue, don't actually calculate the work. There is a condition on the fundamental theorem of calculus. So when we looked at the fundamental theorem of calculus, it says if f of x is continuous on the given interval that they gave us. So f of x has to be continuous. We were dealing with linear functions. They were all continuous. The function I just gave you is continuity. So this is f of x. Where is this function discontinuous? So x cannot be equal to 0, okay? So this function, so this is f of x, and x cannot be equal to 0. There's a discontinuity at x is equal to 0. Is that discontinuity in the interval? Yes. So what that means is the function is not continuous on that closed interval. So what we would say is we would actually not calculate this one, and we would say since 1 over x squared, which was my original function, is not continuous, on that closed interval from -2 to 3, because 0 exists within that interval, the fundamental theorem of calculus does not apply. Okay, let's look at number 3. There's the same discontinuity at x is equal to 0 here. However, does 0 exist in the given interval that they gave us? No. So that means that the fundamental theorem of calculus will apply for 3. Okay? So let's see, I'm going to do 3 down here. So again, there's no quotient rule for antiderivatives. So let's rewrite this one. It will be 2x over x squared plus 3 over x squared. This is equal to 2x to the -1 plus 3x to the -2, because I wanted to do my reverse power rule. Okay. Now something is going to happen when we take the antiderivative of each of these terms. So one of these terms we're going to be able to take the antiderivative of, and one of these terms we're going to come into an issue that you came into in lesson 1. Do you see which term it is? Yes, it's going to be the first term. So if you were to take the antiderivative of this using the reverse power law, you're going to add 1 and then divide by the new exponent. So that would give us 2x to the 0 over 0, which is what we can't have. So do you remember what we did? This is the same thing as 2 over x. Do you remember what the antiderivative of 2 over x was? From logs? Yes. The antiderivative of 2 over x, it's going to be whatever our constant is, ln, the absolute value of x. Because, so let's just think about this for a second. If I said, so let's just write the derivative of ln of x. So if I said from logs, I want you to give me the derivative of ln of just x. Do you guys remember what the derivative of ln of x was? It's u prime over u. ln of x, u prime, is going to be 1 over x. So basically, what you always need to recognize is if you have something over x, the antiderivative of that is going to be the ln of the absolute value. And the reason why we do the absolute value is because we can't have a negative number here. Okay? So again, and how you would see that is you would try to do the reverse power rule and you get something over 0, and then you say, oh yeah, we can't do that, so that's going to be the natural log of x. And then this one here, when we integrate this, we're going to add 1. So that will give us plus 3x to the negative 1 over negative 1. So that will be 2 ln the absolute value of x minus 3 over x. Our integral was from 1 to 2. You're going to sub in f of b minus f of a. So we're going to have 2 ln, absolute value of 2 is just 2. So 2n ln of 2 minus 3 over 2. So that would be f of b minus now, the natural log of 1 from logs. What's the natural log of 1? Anybody remember? E to what power will give you 1? 0. Remember, whenever we have an argument of 1, the answer is 0. So the ln of 1 is 0. So 2 times 0 is 0. So this is going to give us 0. So we'll have 2 ln of 2 minus 3 over 2. And then we're going to distribute that negative over here, and we're going to have plus 3. Get common denominators. And the answer as an exact value will be 2 ln of 2. Negative 3 over 2 plus 6 over 2 is going to be plus 3 over 2. Your calculator would integrate it and give you a decimal, but if you typed in this, you get that decimal. Let's do the last one. And then this is going to see if you guys remember what the antiderivative of cosine is. Okay. So what I recommend doing, if ever you have sine or cosines, I recommend write what the derivative of the function was. So for example, if I said, what is the derivative with respect to x of sine of x? What was the derivative of sine of x? Derivative of sine of x is cos of x. So if I want the antiderivative of cos of x, it's going to be sine of x. So this one here, the antiderivative of 2x is going to be 2x squared over 2, which will just be x squared, plus the antiderivative of cos of x is sine of x. And again, if ever you're unsure, you could then take the derivative of this and take the derivative of this and see if you go back here. Right? Derivative of sine of x is cos of x. We're integrating from 0 to pi. This will be equal to, so let's plug in our upper limit of integration. We're going to get pi squared minus sine of pi, no, plus sine of pi, minus, so that's f of b, minus f of a. So you're going to plug in a 0. You'll have 0 squared, which I don't need, plus sine of 0. Okay. Sine of pi, 0. So here sine of pi is 0. This gives me pi squared minus, what was the sine at 0? 0. This is as well as 0. So that gives me an answer of pi squared. Okay. So for homework for this, there's sort of two things that you could do. Um, from your homework packet, you could do 20 to 25, and then after that, you could do 2A, 3AC on page 454. So you should probably be able to finish in class.